Hi, let me see if I can just get this one done a little bit quicker than that last one. The only thing we're doing in this video is looking at the spread of data. In the last video, we were just talking about distributions and location. So now we want some different measures to talk about how spread the data is in a distribution. And one natural value that we use for this is the variance. Go back down to the definition. Just like the previous video, I think it's easier to understand the variance of a sample first and then go from there to the population. So let's move over here. The variance of a sample, we use the notation as squared. So again, let me just put over, this is for the sample, if you had sample data. And the variance is really just looking about how spread out the data is around the mean. So that helps, I think, to understand the formula here. So what I'm going to do is take each of my sample data values, xi, and I'm going to subtract them from the mean to see how spread out the distribution is against its mean. Now, if I just sum these from I equals 1 to n, it would come out to be 0 because that's how I constructed the mean, so it would be the average. So if I don't want 0, which wouldn't really make sense for the spread, I go ahead and I square this sum. Well, I square the summed terms, and then I'm going to divide by, you would think I would divide by n for an average, but actually in this case I divide by n minus 1. I don't think you should worry about exactly why, but I'm doing it because this will make s squared a better estimate of the population variance. So just dividing by n doesn't quite do as well as n minus 1 does, so that's why I'm doing it, to make it a better estimator of sigma squared. So up here is the population variance, and we use the notation sigma squared, so we're back to Greek language for the population. For a discrete random variable, it's going to look very similar to this definition. Instead of weighting everybody equally likely with dividing by n minus 1, we're going to weight each of the x values by the density function. So this definition, I think, is it's pretty comparable, and just realize that f of x is weighting each of these data values. So I would take the x's minus mu. Mu is the mean of my population, and multiply by f of x to weight each of the x's. So f of x here is serving like the 1 over n minus 1 as the probability that x will occur. So this is for a discrete random variable because I'm summing, right? And discrete means I have values at 1, 2, 3, for example. For continuous, all I'm going to do is replace the sum with an integral. So it's going to be x minus mu squared times f of x dx, and I'm integrating over my support. A lot of times I don't put these values in. I'm just assuming you're going to say, hey, the support is 0 to infinity, but we have to give that to you, so you'll know you'll just use the support values there. So the variance is a measure of spread, how the data is clustered about the mean of the distribution. And let's go ahead, let's look down on this guy, use this little hand. And the standard deviation is just the square root of the variance. And often we want standard deviation instead of variance because the variance is in units squared, and if you take the square roots, then you're in the same units as the mean. So if you take sigma squared, take a positive square root of it, this is your standard deviation for the population. Same way with sample, s squared is the variance for the sample. If I take the positive square root of s squared, I get s. So these are standard deviations. So all we're doing in this example is going back to the f of t that we've defined previously and finding the standard deviation of the time. So by what we said above, if I want to find the expected value or mean of the distribution, oh sorry, we already found the mean, so I don't need to do that, right? If I want to find the variance of the distribution, what I'm going to do is integrate my t's minus mu, which was the population mean, which we found in the last video, times f of t dt, and this was defined for all positive t's, so 0 to infinity. I'm just going to go to Maple right now and do that. I think I already, sorry, in the last video I did. Let me go ahead and get rid of this, because I've made this video a couple times, so I already computed it. Anyway, we already have mu from the last video that we did. That's the mean of the population. So if we want the variance, that's just going to be the integral of f of t times minus mu, and I'm integrating from 0 to infinity, which was the random variable support. So that's variance, and if I want the standard deviation, I just take the square root of the variance, and this will be my standard deviation for that example. Okay, pretty nice. Going back, that's how you do it for a population. And for a sample, I showed you the formula, but another measure of spread for a sample is called the IQR, which is interquartile range. I guess he already said there it is. What I'm going to do is subtract Q1, the first quartile, from the third quartile, and that difference is the IQR. So it's really a measure of spread, but more for the data being clustered about the median instead of the mean. And natural measure, a way to see this, like visibly see this, is through a box plot. It's really the nicest graph to look at the IQR. And compared to the standard deviation, that we say the IQR is more robust or stable. If you just delete a few values here or there, the median will stay pretty close to the median in the same way with the interquartile range. But for the variance, if you make some small changes, especially if they're on the extreme values, you could get a very different standard deviation. So IQR pretty stable. And down here, it just says let's use the data we have in Minitab from example 6. So here it is. I went ahead, let me just show you what I did. In Minitab, I took the data in weeks, and I just asked Minitab to sort it from high to low. So the value here, I think there was a 7 and a 10. What I did is went ahead and deleted the first 2 points, and then I went down here and deleted the last 2 points. And I asked Minitab to replot that box plot. So you can see right here, I mean, it has changed. The interesting thing, there's the mean, 64.125. Now I took off the top 2 and the bottom 2, and the top 2 are pulling that guy out to the right. So the mean now should have, I want to say, shrunk. Before it was 64, and now 62. So that has changed, and statistically would say, I mean, quite a bit for that small data set. And they were already fairly clustered, and the interquartile range, let's go back over here. The interquartile range here is 46, and the interquartile range here is 45.5. So not a huge effect on the median or the IQR. So yeah, this is a little bit better measure if you have skewness and you start taking away values. IQR will stay pretty true to the original IQR. So that's the end of this video, and I think the next one is just normals, and at least we cut off a little time. Okay, talk to you in the next section.